Okay, guys, I hope you can hear me. We've got a little bit of time before the lecture starts, so if there are any questions related to the lecture, the homework, feel free to shoot.
Hello.
Yeah.
I submit the correction of homework 1 with the second homework, but I haven't got any feedback yet. Should I just wait or send an email to the TA or?
Will you? When your TA grades the second homework, is going to update the first homework. So I don't know when Samantha is going to get the second homework graded.
I already got the grade for the second homework, but
okay, well then you should reach out and see if what's going on with the first homework.
okay.
Hi, Professor.
Hello.
So we're supposed to submit one file, but the Excel for the Monte Carlo simulation is like a separate file from the homework. Do you want us to submit just the results for the expected values or compile the file into a PDF? I'm not sure how to do that.
You can do either one.
Okay.
If you just report the numbers from your Excel sheet, maybe I could share my numbers so you can just make sure that you're in the ballpark.
Okay.
Right, you have two ways of computing the numbers, right? You have the analytic formula, and then you have this simulation thing. So let's see. It's this question here about Monte Carlo and computing the Black-Scholes formula. This is formula number 1.
Yes.
I'm getting numbers that look like this.
Okay, I'm in the ballpark.
You're in the ballpark, yeah. So don't be. It depends on how efficient your Excel sheets are running, how many simulations you do, and so on. This class here is not about simulation. It's just to give you an idea about like how one could try to compute numerically an expectation like this one. When you get into like computational finance and these courses, then there'll be a lot more problems and theory about Monte Carlo simulation.
Thank you.
Okay.
Professor, for the first problem on homework, I looked up the Black's formula.
Yep.
From 1976, and I didn't look similar to the result I got. So I was kind of wondering if I did it correctly or not, or like what you meant by Black's formula.
Black's formula, but it's the. Let me switch over so I can have my.
Because when I looked it up, there was some like partial differential equation, and no. I was like, this probably isn't what I'm looking for.
No, you're looking for. So let me get this thing on here. Right, so you're interested in computing this expectation of e to the sigma x minus 1/2 sigma squared minus a constant and then positive part. That's the one you're interested in getting at. And so what I would like you to do is to convert this expectation into a Riemann integral. And so you will be, instead of, so x is standard normal. So what you do is you replace the random variable by a dummy. And then you replace the expectation by an integral. And so now you're going to be integrating all possible values of the dummy. So this is going to be in the, right here you're performing your random variable as domain omega. Here the integration is performed over omega, and now we're switching over and integrating over the codomain. So here we're going to be integrating over R, and then you need density. So this is 1 over root 2 pi e to the minus x squared over 2 dx. So this is, work out what this thing here is. And whatever you're going to get, this is going to be Black's formula.
Gotcha. Thank you.
Okay. More questions or comments before we get started? Okay, then then let's get started on the lecture. Last time we were talking about random variables. So recall that this function is a measurable function. So this is what we call a random variable. It's a random variable if I look at the set. So I take a point in the codomain. This set here belongs to f for any value in that codomain. And also, and if I look at sigma of x, and sigma of x denotes the smallest sigma algebra, such that these sets these level sets that they are inside sigma of x. Okay, so so that's a random variable. It's a measurable function. It has this property. Okay. And what it allows us to do, the reason that this property is so important, is because we can then talk about. So we can then talk about. X's distribution. So this is when I measure these sets, or even or more general, if I look at P of X in a set B, and B is a Borel set. Right, so now what I know here is that this set here is going to be inside F. So I can look at that means that given that X is measurable, this set, this level set of capital X less than X, this is going to be inside F. P has domain F, so this quantity makes sense, and this is going to be what I'll call the distribution function. Okay, and so that's the distribution, and then we say X has a density. X has a density if has a density F if I can write f of x as an integral from -infinity to x of f of y dy. And this is true for all x. Okay, so it's important to have this measurability property because it allows us to define the distribution. Okay. So what our goal, so tonight's goal is, to define this expectation of x. For positive random variables. So now x goes into the positive numbers. And then later on, so later we extend to, well, there are two important extensions. So the first one is we're going to extend to both positive and negative random variables. And more importantly is we're going to allow for conditional expectations, not just the expectations we have up here. We're going to extend it to give meaning to this quantity where a G is a smaller sigma algebra than necessarily F is. So this is a conditional expectation. This thing is called the conditional expectation of x given G. So you've probably seen that that formula we had in one of the questions. You've probably seen that you can compute expectations of x. You can compute the expectation of x as a Riemann integral of x f of x dx when x has a density f. You've probably also seen a formula of sorts where, if we move into the second part here, you've probably also seen a formula of something like, sometimes you'll see people write stuff like that. You've probably also seen a formula for this one when x and y have a joint density. So what's going to happen now is that we'll discuss these types of expectations without necessarily having densities available. So it'll be a more general theory than what you probably seen before. So we're not going to be relying, in what follows now, we're not going to be relying on densities. Of course, whatever we're going to do has to have the property that it's consistent with what you have seen before in the case that it has a density, right? So this more general theory that we're going to develop is going to have this property that if I specialize to the case where there is a density, well, then I have to get the theory, I have to get the same results as what we've seen before. Okay, so we're not going to create any sort of inconsistency. Like this condition expectation that you're used to, this is going to be a special case. It's going to be a special case of the more general conditional expectation that we're going to talk about probably next time on Thursday. Okay, so tonight the goal is to figure out, write down a definition of this expectation, and then I have a handful of examples I want to look at. Yeah, I can repeat what G is. G is a given G, so G is a sigma algebra. Which is it's not bigger than F, right? So this is not bigger than F. Yeah, G is a sigma algebra, and it's inside F. F is the big universe that we live in, right? X is given to be F measurable, right? So I'm looking here at something that's smaller. Okay, so let's get started on this one. And the way that we're going to do it, the way that the Lebesgue integral so this is the one we're going to create now, the Lebesgue integral. This is this expectation. So the way that it goes is you start with simple, also sometimes called elementary random variables, and then you extend to general ones. So I'm going to start calling these RVs. Okay, so what is a simple and or an elementary random variable? Well, so we say that X is simple if I can write X at a point omega as, so I need to be able to find constants, we call them yi's. So I'm looking at positive random variables. I'm going to be finding positive constants. If they exist yi's and there exists ai's, these ai's, they have to be measurable, so yeah, sets in the sigma algebra. And I want to demand that they are disjoint. So I can find disjoint measurable sets such that X can be written as a sum, and this is going to be a finite sum over these yi's times the indicator for ai. Okay, so this symbol here, this indicator here, so we have a constant, and then we have this indicator here. This might be new to some of you, so where 1a of omega denotes, this is called the indicator function, the indicator function of a set. And so what does that mean? Well, 1a of omega, this is defined to be, hang on. Excuse me. Oh, where were indicator for the function? So that means that it's equal to 1. Is equal to 1 for omega in A, and then it's equal to 0 else. Okay, so we say that a random variable is simple. If I can write it as this finite sum.
Professor, what's the superscript on this on the sum symbol? Is that an M?
Up here?
Yeah.
That's an M. This is just for some M, which is a natural number. Like it's a finite sum. Not an infinite, it's a finite sum.
And the disjointness, you said AI intersect
And
AJ.
should be empty.
Gotcha.
So the immeasurable and the disjoint. So what's happening here is that I have my omega. So we make an omega down here in the corner. This here is my omega. I'm going to say that x is simple if I can somehow decompose, say, into here 3 sets, A1, A2, A3. And so on these 3 sets, let's call them cells, or let's call them blocks, partition components. So on each of these blocks of omega, the random variable x is constant. So within these AIs, the value of x is going to be exactly yi. So on a I, x is constantly equal to yi. There's another question here. The superscript over the summation is mu or m? Just, yeah, I mean, either one. This is just some symbol that I use to indicate the size of the sum. So I had intended this to be m, right? So it's just some m in n, but you can call it mu, it's okay. Just some finite number. Some finite number, yeah. Okay, so now what we want to do is, this is where we start. We start with these guys. We need to figure out what is the expectation of such a thing. Okay, so we need the expectation of a elementary or a simple random variable. Okay, so it's a sum. Okay, we expect the expectation is going to be linear, right? So a finite sum, we can pull out the sum. And these are constant, expectation of constants. They can also go outside. So we really just need to understand what the expectation, we need to define what the expectation of an indicator is. So we define the expectation of this simple random variable to be, we'll pull out the sum of these yi's, and then we have the expectation of these 1ai. Okay, so I need to give meaning to what should the expectation of 1ai be. But this should be, what should that be? So we're going to say that this here is exactly, this is exactly, so this is exactly the probability of AI.
Oh, it's because you have 0 times the complement and 1 plus 1 times the probability.
So this is a definition, right? So we could have defined it however we wanted, but that's the point, that on the set AI, the indicator is equal to 1. Okay, so you're going to get 1 times the set plus, okay, so on the complement, the indicator is 0. So you're going to get 0 times the probability of the complement, so that's 0. So this is the definition of what it means, of what the expectation operator means for an elementary or a simple random variable. So far, so good. So now the question is, how do we extend? How to extend to arbitrary x, and I want to restrict still to be even positive. Okay, let me try to think about. We'll try to think about the. So before just giving the definition, just maybe some intuition for why we're doing what we're doing. So if you do the Riemann, the way that the Riemann integral is created is you're looking at a function, something like this, and then we're looking at approximating the function, maybe by these step functions. And so we're somehow approximating the function f by this these steps here. And so we are splitting up the x axis. So here we have 0, here we have x1, here we have x2, here we have x3, we have x4, and so on. And so what we're doing is we're approximating this arbitrary, in this case, smooth function by constant values on these subintervals. And so we're splitting f's domain. And then within these cells, we're keeping f constant. So that's how the Riemann integral goes, right? And then we're computing the area of these. It's easy to compute what the integral of the step function will be because it's flat on each interval. So you take the height. So the height is f of xn. Then you take the width. This is delta x. You say that this is delta x, and then you sum them up. This is something that you want to think about as approximating the integral. Okay, so this is not going to work for us because, so in our case, x's domain, this is omega. X's domain is not easily broken up into the same fashion as you can break up the positive real line. This is not, and not always, R, or a subset of R. So the idea in the Lebesgue integral is, it might very well be that x's domain is omega, but so the bright idea is to split not x's domain, but split x's codomain. Okay, so how does that work? So let me look at a little example. So here's an example. So this is the y-axis, right? Whereas, like the codomain is out here, domain is out here. So for the Riemann integral, we're splitting the domain. We're not splitting the codomain, what we're saying now is for the big integral, we're going to be splitting the codomain, and we're not going to worry so much about the domain for now. So how would one go about doing it? I need a good way to split this codomain. So here's a way to do it. So split x's codomain. And this is R, or for now, it's these. We're looking at positive random variables, so we're only splitting up the positive one. Okay, so what could be a way to split it? But here I just wrote delta x, but how would I actually choose these points here and then put them out on the y-axis? One way to do it is use these numbers here. You will see them a lot in books on integration theory. You would have, you look at I divided by something like 2 to the n. So you pick a number, and then I look at this sequence here for I going from 0 to n times 2 to the n. So here I'll have, say, I minus 1 divided by 2 to the n, and here I'll have I divided by 2 to the n, and then it would run. So for example, if I have n is 2, what would I get here in this sequence? The first number would be 0, and then the next number would be, well, 2 squared. This is 2 squared is 1 over 4, so I get 1 over 4, and then I would get 2 over 4, and so on. And the last one will be I equal to n times 2n, so it'll be equal to n. So the last one will be 2. And if I go up to n equal to 3, then what's going to happen? I'm going to start out at 0 again. Right, this is because I'm splitting here from 0 to infinity. So if I go, what will be the next one? That'll be 2 to the n, that's 2 to the power 3. So this is 2 times 2 times 2, that's 8. So I'll get 1 over 8. And then the next one will be 1 over 4, and so on. And it will go all the way up to 3. And you can see this here is a finer partition than that one, right? I'm going to have an inclusion here. Right? This is a finer mesh compared to the previous one. So what's happening is that I have whatever mesh, and then I throw in twice as many points. And not only do I do that, instead of going out to 2, I'll go out a little bit further. And then I'll go out a little bit further, a little bit further, a little bit further. So this is one way to split this integral 0 to infinity using these numbers I have here. Some of you have probably seen this way of creating a mesh in other courses. It has a name, but the name escapes me. I don't remember it. So then what? So then we can approximate. So now we can try to approximate. We can now try to approximate x by the simple xn. Approximate x by simple xn's. Okay, and we know how to compute. We know how to compute the integral. We know how to compute the integral of xn because it's simple, and so if we can approximate x by these simple ones, we might be able to get the integral defined for this general one. Okay, so how would we do that? I need to create the simpler ones. Need to create the simpler one. So if I'm looking at xn of omega, this is going to be it's going to be a sum. It's going to be a sum from I equals 1 to n times 2 to the nth. That was my upper limit point. So I'm gonna run through I equals 1 to 2 to the n, and so I need my sets. What should my I be? And so I need values here, and then I need this indicator of my sets. So it'll be I n. I need to figure out what to put here. What are these sets? So A and I. This is going to be how I split the omega, and I'm going to use split omega according to how I split the codomain. I'll look here at these omegas such that the random variable I'm trying to approximate, x of omega, takes values between, say, I minus 1 divided by 2 to the nth, and then I divided by 2 to the nth. And so I'm splitting according to where x's value is. And of course, for a given n, it only runs up to n. So there's also a chance that x is going to be really big out here. So I'll create like the last one. This is those omegas such that x is big. Okay, so that's going to be the indicator. And then I have to decide on these cells, what should I approximate, what value should I approximate with? And so the convention is to use the lower bound here. This is going to be I minus 1 divided by 2 to the nth. And then there's this chance that x could be huge. So I need n here. There's my lower bound on that last one, 1 a n of omega. So then we have some properties. We have one that they are increasing, xn increases. So you get bigger and bigger and bigger, and you're always less than x. That's because I chose the lower bound when I assigned the value here. And the other property we have is actually if I compute the limit as n goes to infinity of these guys, xn of omega, I actually get exactly x of omega. And I also know how to compute, the expectation. If I am to compute what the expectation is, by definition, I know how to do that. It's a finite sum, so I'll pull the sum outside. So it's n to the 2 to the nth, I minus 1 divided by 2n, and then I'll get the probability of a I n plus n times p of a n. So how should we define the expectation of x?
Professor, can you explain this? I'm a little confused about this construction, this splitting idea.
Yeah.
So is what we're doing splitting it into smaller and smaller subsections as n increases?
Yes, and that is exactly what's happening. Right? We're splitting the y-axis. We're splitting the y-axis into smaller and smaller sections. Because we start out, if you plot these ones here on the y-axis, like here I would have my omega, and so here I would have points like 1 over 4. I would have a half, and so on. And then for the next partition, I would have the same points, and here I would stop somewhere up around 2. And then for the next partition and higher value of n, I'm going to throw in even more points. And I'm going to keep the ones I have, and I'm going to throw in more points. And now I'll go all the way up to 3.
So the final one, does it cover all of the positive real numbers?
There's no final one.
Oh, it just keeps on going. Okay.
There's no final one, right?
Right, yeah.
There's
It's
no
like a limit.
yeah, but this is the big. That's a like here. N is in the natural numbers. Like there's no n equal to plus infinity because this thing doesn't belong to n. There is no final one. That's the problem.
So how are we thinking about x? Because we have like x n plus 1, and then you have like
so far we have gotten this thing here created. We have gotten ourselves an approximation created, and the approximation has this property that when I put in more and more, when I go to a finer and finer discretization of the y-axis. So when I throw in more and more points on the y-axis, I get an increasing sequence of random variables.
But the random variable at the, see, this is why I was confused. The random variable at the end, I was thinking of that one as the final one, but like does like each random variable correspond to one of these meshes?
Yes.
Yep. So which one does the last last one?
There is no last one.
But there's one in property I, right? This on the right hand, the rightmost one. Yeah, that one.
No, but this is what is given.
Oh, it's given. Okay.
This is what is given, right? This is what is given. We're trying to figure out how should we define the expectation of x.
Gotcha. Okay.
So x is a given random variable. We're trying to figure out how should we define its expectation. Currently, the only thing that we have defined is expectations of these simple or elementary random variables. I haven't defined what is the expectation of x, because x is not simple. It doesn't have this form that it's constant on these cells. xn has that property, right? xn is constant on all these AIs. And there are finitely many AI for a given n. There are only finitely many of these AIs. The question is, how should we define the expectation of x? At least I got myself a sequence here, right? And so given that x increases, the expectations will also increase, right? You're going to get these numbers here are going to become bigger and bigger and bigger as n goes. So these expectations are going to have a limit. And the question is, can I use that to define the expectation of x? So however we define this expectation, we should have that this expectation here is exactly the limit as n goes to plus infinity of e of xn. However we define it, we should have this property. Are we guaranteed for it to converge as n goes to infinity? This was a question in the log. Yeah, so if I have monotonicity, then if I look at if x is smaller than y and x and y are simple, then the definition of this expectation of x and the definition of the expectation of y when x and y are simple, if I have an ordering between x and y, then the expectation is going to preserve that ordering. So these expectations here, they are increasing as a function of n. And therefore, if I have a monotone sequence, it's going to have a limit. So it's going to have a limit, but this limit, it's going to be a bunch of positive numbers. So the limit is going to exist, but potentially it's going to be equal to plus infinity. It could explode. So yeah, we guarantee that it exists, but it could be plus infinity. And we're going to see an example later tonight that it can easily become plus infinity. Even though all the expectations here are finite, the limit could perfectly well be plus infinity. So that's not guaranteed. So however we define this, we should have this property here. Okay, so here's the definition. So all this example here does is that this serves to motivate how one can go about computing the big integral of an abstract random variable. Right? So it's a little bit like if you were to compute the integral of a function, you can always go back and approximate with these Lec6 with these Riemann upper and lower sums and compute the limit of those, and that's going to give you this integral. What this here shows is that if, at least in theory, if you were to compute an expectation of an abstract random variable, you can create these xn's and compute the limit of their expectation. It's gonna give you the number that you're looking for. So now I'm going to write down the abstract definition of this expectation, and then the first theorem that we're going to talk about is going to be such that this property is true. And it's important here that we have monotonicity. So this here is a definition. This is called the big integral. So we have a random variable that is non-negative. For this guy, measurable, we define the expectation of x. This is defined as a supremum of e to the y, such that, well, y is going to be simple and it's going to be less than x. So that's the formal definition of the Lebesgue integral of a random variable. And there's this supremum in here, and I'm not sure if everybody has seen what a supremum is, but just in case you have not seen a supremum, let me just maybe briefly look at what that means. If I look at, so recall that if I take a supremum, A, say, where A is in some set capital A. So what is this? This is a big this is a big number. What does it mean? This is the smallest big number. Okay, so what does it mean to be a big number? What does it mean to be a big number? It means that the supremum of, I said A, is big. It's bigger than every single number in the set. But that's what it means to be a big number. It's bigger than everything else in the set A. And it's the smallest such number. And if say B is bigger than A for any A in A, well then B is also going to be bigger than the supremum. Right, so this is a big number, and then the smallest big number is this property here. So the supremum of a set, it is a number, there's a quantity that has the property that it dominates everything in the set. And there's nothing, and it's the smallest such thing. So if you can find another thing that dominates it, that supremum is going to be small. Right, so as an example, if I look at the supremum of, say, 1 minus 1 over n, n running through the natural numbers, what would that be? Well, it's a big number. So it's something that's bigger than
The 1.
So would that be 1? Right, so you can get arbitrarily close to 1. So if I picked another number over here, say I picked 2, right? 2 is also going to be bigger than 1 minus 1 over n for all n. But 2 is not the smallest such number. Right? I could do 1.5 and that would also work. And you can go all the way down to 1. But note, we cannot find an n such that 1 minus 1 over n is equal to 1. Right? So there's no max. You cannot find an n in here that contains this maximum. We only find the supremum. And likewise, you can define the infimum, right? So an infimum, this is a small number, right? So an infimum, when you write I and F here, an infimum, this is something that is smaller than anything in here. And it's the biggest such number. So it's a big, small number. Sometimes, yeah, so this is the definition here. And please note, we're not claiming that the supremum here is attained, and this is typically not a max. This is just like this example down here. The supremum up here in the definition of the Levig integral, this is typically not a max. So there is no simple function that's going to attain this supremum. Just as there is no n in the natural numbers that's going to attain this one. One could ask a question. So this here is going to be, a number between 0 and infinity, and this one included. It could be plus infinity. So one could ask, can I always just take a supremum? Like we talked about, we cannot always take limits. Can you always take supremum? And the answer to that question is yes. If I am working on an interval like this one, or if I'm working at, this extended real line, I can always take a supremum. These supremacy always exists. So this number here, this is a well-defined quantity. This is a big number. The supremum here is bigger than these expectations. And it's the smallest such big number, it could potentially be infinity. Oh, I see there's some. Does the E operator mean integral expectation? This is the same. This is tomato, tomato. There are many ways to write this expectation here. So there are other ways to write this expectation of X. The include, there are probably even more. The include, writing like an integral of X and then write the P here. You can do that. You can write it as X of omega, and then sometimes people put an omega down there, and then you write dp and then put an omega in here. Or you can write, some people like to write this in a different order. So you can write this, and then you can write P of the omega. There's a very, very old way to write it, or if you go back to some of the old in particular, right, probability, the type of probability that we're talking about, this is, it originates from the Russian school in Moscow. It originates by Kolmogorov. And so there's a huge tradition in, and continues to be a very strong presence of probabilists centered around Moscow. And D didn't write E's, D wrote M. But this is old school. It's been a long time since I've seen papers published that write M, but there are textbooks out there that'll do it. M stands for mean, so he would do that. But yeah, so when I talk about Lebesgue integrals, for probabilists, I shouldn't say we here, but probabilists don't write integrals so often. We like to write these expectations. People in analysis, they like to write integrals, so they write integrals. This here is a Lebesgue integral. It's just written with an E. Is there another question in the chat? Can I give another example of soup? I mean, yeah, if I take, sure, if I take supremum over n in the natural numbers, what would I get here?
Are we working with the extended real line?
Yeah, so what would I get?
Infinity?
I'll get plus infinity. Yeah, I'm hoping we're not too afraid of working with infinity. This is something we are going to be doing quite a bit of, right? So don't be afraid of working with plus infinity. We need to have a somewhat of a reasonable relationship to working with plus infinity, right? The thing that you cannot do with infinity is you cannot take plus infinity and minus infinity, right? So stay away from that one. Other than that, we're good, we can work with infinity. We cannot take plus infinity, minus infinity, so stay away from that one. And the reason we're working with these positive functions for now is that we want to avoid exactly doing that. So that was another example. Let's see. So if you were to take a PhD course in integration theory, you will see this definition, and then immediately after you'll get to the crown jewel of the theory, and the crown jewel with absolutely no exception. This is the following result, which is called the Lebesgue's monotone convergence theorem. And this is by far the crown jewel of the theory. This is where everything comes from this theorem. And what it says is that if I take, so now I have my definition for arbitrary positive random variables. So if I take a sequence of random variables, so x1 of omega is less than x2 of omega is less than this all the way up. If I take a monotone sequence of these random variables, like the one we created, yeah, then the monotone convergence theorem says that if I compute the limit, and again, I have monotonicity, if I compute the limit of these expectations, this is a monotone sequence, so I can take a limit. This thing is the same thing as pulling the limit inside. And again, this is also a monotone sequence, so I can take a limit. So both these things make sense. And the monotone convergence theorem says that they're actually the same. I can pull limits inside expectations if I have monotonicity. So I'm going to be giving you guys a few examples discussing this. We're not going to be doing the proof of the Lebesgue monotone convergence theorem. It's not, I won't say it's like super hard. It's a little bit tricky, but it's not like outrageously long or difficult. It's also not trivial. If you Google Lebesgue's monotone convergence theorem, you will get many teaching notes, and you can have a look there. Wikipedia has a site on it. I'm sure you can find YouTube videos that will discuss the proof and so on. This is easy to find material on. Okay, so instead, what I want to do is I want to try to look at a few examples, discussing, illustrating maybe some of the things that can go wrong. Are there any questions before we get to that? At least at this point, we managed to write down a definition of an expectation of a positive random variable. And it does not involve the density function at all. And so we somehow also have to prove, at some point, we have to prove that this way of defining an expectation is somehow consistent. Remember that was the starting point. This formula here should somehow be consistent with what you have seen in probability. If there is a density, so here's a definition of x, expectation of x. This definition has to be consistent with what you have seen in an earlier probability course when x has a density f. That formula you have here has to be exactly the same as the supremum that you have here when x has a density f. I mean, otherwise we're creating problems, right? We're doing stuff that is inconsistent. And this is the truth. This is really the case that when x has a density little f, this supremum over here, however messy it looks like, this is going to become exactly this. So I'm claiming that's not completely obvious, and this is probably something we should think about and ultimately try to write down a proof of. Okay. So some examples related to the conclusion of the Lec6 monotone convergence theorem. So let's do some examples. I have a few prepared. I'll find them. So if I do, what we could do is we could look at functions like these ones. So let me look at the interval from 0 to 1. And so I'm looking at a function. This is my f1. It's just constantly equal to 1. And then the next one, I'm going to double up and go up to 2. And then the next one is going to be 1 over 3. And I want to go up to 3, and so on. Right? So I'm going to look at, this was f2, and this was f3. I'm going to look at fn of x. It's going to be equal to n when x belongs to 0 to 1 over n, and it's going to be equal to 0 else. Right, so my omega here, I'm just going to take it to be the open interval from 0 to 1. Right, so these here are the uniform densities. And so when I integrate them, I'm going to get that this is n times the integral from 0 to 1 over n of a 1 dx. And so that's 1, right? It is a density, it's a positive function, it integrates to 1, it's a uniform density. But if I look at the limit as n goes to infinity of fn of x, what do I get here? I pick a point x between 0 and 1, so let's find one up here. If I pick a point here, let's say that this is my x.
Does it go to 0?
It's going to go to 0. So the limit is equal to 0. Obviously, then the integral is going to be, if I integrate the limit, then this is also going to be a 0, right? But if I pull the limit outside, I'm going to get the limit of these fn's, they all integrate to 1. Right? So this here is different from the limit of fn dx, because this is equal to 1. So you see this thing about pulling limits inside and outside intervals. This is something one should be pretty careful about, because 1 is definitely not the same as 0. And it's this sort of a property that we can avoid. It's this kind of behavior that we can avoid if you have monotonicity. Like here with my functions, so we should just note we don't have that fn of x. This is not less than fn plus 1 of x for all x in the interval 0 to 1. Right? This is not true. These functions here, they're not monotonically increasing in n. Right? Indeed, you see something like, you see what happens here at the point x, right? So you go first it's equal to 1, then it's equal to 2, and then it's equal to 0. Right? So it's 1, 2, 0. This is not monotone. These functions, they don't monotonically increase. So that was one example of what could go wrong.
Wait, what's 1, 2, 0? You say that again?
If I pick my x here, I pick that x.
Oh, I got you. As you vary the n, it becomes 1, 2,
So first
0.
is 1, right? And then now look at f2 of that same point. It's going to be 2. Right? And then I'll look at f3 of that point. So say that x was in between here, right? So then it's going to become 1, 2, 0. Whereas if I moved it over here, so now it'll be x0, then it'll become what? It will become 1, 2, 3. So it looks promising, right? It's monotone, 1, 2, 3. But then at some point, this n is going to scooch by here, and then it's going to drop to 0.
Oh, so it's going to be increasing and then it just drops to 0. So it's not monotone.
So it's not monotone.
Are we looking at the same point x?
It has to be for all x, right? It has to be for all x.
Okay, you're comparing the functions using one x, but it has to apply for all the.
Yeah, so you pick an arbitrary x in your in the domain, and then it has the same thing is true here, right? You pick an arbitrary omega in your set, right? This here is for all omega. Now you pick an omega, and then you just look at, do we have monotonicity when you fix that omega, and then you vary the parameter, the n parameter down here, do you get a monotone sequence? So we need that if you want to have that conclusion. And here we don't have it. We also don't get the conclusion, so it works. I had one more prepared. So this here was a uniform. So you see, it doesn't take much. I can make it fail for uniform distribution. So I'm going to pick another one, which is also something that you guys have I've already seen. Let me share my screen so you can see. If you look at this one here, the second homework, you're playing with the exponential. Here we have the exponential, right? So you pick any alpha that is positive. This here is a function that's the exponential density, right? So that is positive and it integrates to 1. Now I'm just looking at x's that are non-negative. Okay, so let's see if I can make it break for the exponential. So another example would be, let's look at f. So here omega is the positive line. So let me look at fn of x to be, let's say 1 over n times e to the minus 1 over n x. And this is for x in omega and for n in the natural numbers. So because of the exponential density property, when I integrate, I'm going to get 1. However, if I look at the limit as n goes to infinity of fn of x, what do I get here?
I think it's gonna be in
Shouldn't it be 0?
Yeah, we can use the sandwich theorem, right? We can write that this here is less than this exponential part here. This is a positive number with a minus sign in front of it. So e to that thing is going to be less than 1. So I get that this is less than the limit of 1 over n, which is 0. So we have exactly the same problem as before. If I am to integrate from 0 to infinity of this limit,
wait, did the e to the negative 1 over n vanish?
it's just bounded by 1, right? This quantity here, this is bounded by 1.
Okay.
Right? Because it's a positive number with a negative sign in front of it, so it's a negative number. The exponential function evaluated at a negative number is going to be less than 1. So this is bounded by 1, so I get a bigger number, and then 1 over n is going to give me 0. So it's the same situation as what we had before. So obviously, this sequence here is not going to be monotone, because if it were, we would have to have these two limits to be the same. Are there any more questions or comments on this one? So we have a little bit of time left. The next example is a bit more elaborate. And it's much closer to what we're gonna, this stuff here is what we're gonna be needing in the second half of the class, where we're playing with a continuous time model. So the first half of the class is about the binomial model. So the next example is about the binomial model. And it's kind of on a twist on the binomial model. So this is the, so on an infinite coin space. So this is, so what does that mean? So we say omega is an element there if I can write omega as an infinitely long vector. So this will be omega 1, omega 2, omega 3, and so on, with omega n, so the nth component, being the outcome of a coin flip. So this is going to be either heads or tails. So our sample space now consists of all these infinitely long vectors, where on each component you either have an h or a t. So that's our sample space. And what it amounts to is like an infinite tree and so on. So we want to have an infinite tree and it just keeps going. So start out here, then it just keeps going. This is our infinite coin space. So a natural question to ask is omega countable?
Is the space of omega given by what W can potentially be,
So
or little omega can, like, is it the sequence of HT at H's and T's?
yes, it's sequences of H and T's.
I think you because you can enumerate every element in the sequence, right? And then it's either H or I think it should be countable.
Can it be countable even though it's an infinite coin space, or
like the natural numbers are
yeah.
countable?
Yes,
Countable means there's a bijection between the natural numbers and.
so can we find a bijection if so you're looking at infinitely long strings of H and T's. So try to think about it. Just think about it for a minute before I give you the answer. So some of you some of you say yes, and some of you, if you haven't made up your mind, try to think about it.
Well, are there a countable number of binary numbers? You see where I'm going?
Yeah, so now you're rephrasing the question in terms of a curly question. So yeah, I mean, so can you answer that question? So given the time is clicking, the answer here is no. It's not countable. And let me just, this is not really a class on this stuff, but it is one of the coolest things. It's not one of the coolest things. It is a pretty cool thing, the argument for why this is not countable. And I really believe that this is something that should be, we should enjoy, because there are not that many cool, I mean, there are lots of cool things in math, but this is really one of the, it's so simple. The argument is, so make no mistake about it. This was not an easy thing to do, but when you see the argument is pretty slick. Right? So this is a famous argument due to Cantor, and it's Cantor's diagonalization. So what he does is say it is countable, and then list them. So the way he lists them is you say omega 1. Okay, that's the first element I have in there. I can write this apparently as a long vector of either T's and H's. So I'll list them as W11, W12, W13. So that was the first one. And then you list the second one. This is W21, W22, W23, and so on. And you keep doing this. Wn is equal to Wn1, Wn2, Wn3, and so on. And you keep doing this as far as you can. There's a list of all these things. So Cantor, he said, let's do that. Let's assume that it is countable and list them. And so here comes the trick. Cantor's trick is then to create an omega, not, so maybe we should call it star, not on the list. And how is he going to do that? Well, here's the trick. He is going to look at the diagonal. So keep in mind, W11, this is either H or T. And so what he does is he flips it. He says, flip the diagonal. The diagonal is this humongously long thing that lives down there, right? So flip the diagonal. So you're going to flip this from H to T or from T to H. He's going to do that. He's going to do the same thing with the next one. He's going to do the same thing with the next one. So the next one is W3, 3, W4, 4, and so on. He's going to flip all these elements that he finds on a diagonal from either being a T to becoming an H, or from being an H to becoming a T. And now this element here, this W star, this is nowhere to be found on the list because it at least differs. It at least differs at this one particular point, right? This W star is not equal to W1 because it differs on that element. This W star is not equal to W2 because it differs on the second element. It's not equal to Wn because on the nth component, if Wn was T, then W star is going to be H. If Wn was H, then W star is going to be T. And so that's it. That meant that the contradiction.
Sorry. So this is after the fact of flipping the diagonal, right?
Yep.
Okay.
Yeah. Right. The diagonal elements are W11, W22, W33, and so on. Those are the diagonal elements. Right, so he's going to define this thing here. Right. So.
Oh, so it's like saying, suppose it was cannibal and we enumerated all of them, we can still create another one that's not in the list.
Yeah. Right. This W star is going to have these components with W1 star is equal to T if W11 is equal to H is equal to H if W11 is equal to T, and then W2 star, this is going to be equal to T if W22 is equal to H is equal to H if W22 is equal to T, and so on. And so I'm just flipping the elements on the diagonal. That new W star, this is going to belong to my omega because it's a sequence of H and T, so it's in there. And it's nowhere to be found on the list, so we have a contradiction. So the infinite coin flipping space, it is not countable. It's just it's a good thing to know. If you're in computer science, their H and T's are typically swapped out with zeros and ones. And maybe that will be easier to accept if I just put so my omega would then be strings of zeros and ones. And then you can ask yourself, if I have infinite strings of zeros and ones, what kind of numbers can I generate? Like if you're looking at, if we say that H is equal to 1 and tails is equal to 0, then infinite strings of zeros and ones, how can I generate a number, right? So if I pick for a number x somewhere between 0 and 1, can I write x in terms of zeros and ones? Well, what would I do is I would have a 0 point something. And so here I would have omega 1, I would have omega 2, I would have omega 3, and so on. And what the first one would keep track of would be halves. The second one would keep track of quarters. And the third one would keep track of eighths, and so on. And so the question is, if I take an element, a number between 0 and 1, can I find a half, a quarter, an eighth, a 16th, and so on, such that when I line them up after each other, I get exactly x? And the answer is, yeah, you can do that. I can do that. That means that I can express all numbers between 0 and 1 in terms of these infinite sequences of zeros and ones. Okay, so that means that my space has the same cardinality as the interval 0 to 1, and that is strictly bigger than the cardinality of n. So that's another argument for why this particular binomial model that we have here is uncountable. The last thing I want to do is an example. There was one example on this space that I want to do, and it's what the textbook calls the St. Petersburg paradox. And I'm going to create a random variable. I'm going to create a random variable x. So it's going to go from omega into the positive numbers. And the way I'm going to create x is just going to be in a tree. We don't have very much time left, so I'm going to look at the first coin flip. It's either going to be heads or tails. Okay, so the random variable I'm interested in creating, on this top branch here, I'm going to give it the value 2. And if it's tails, then the next coin flip is either going to be heads or tails. If the next coin flip is tails, then if the subsequent coin flip is heads, I'll give the random variable the value 4. So on all these branches that come out here, it always has the value 2. On all these branches here, it's going to have always the value 4. And then I'm going to keep doing this, so it'll be 8 on this part of the tree. And then if I get TTT, so then again, if I have 3 tails, if I get a head, whatever comes after, I'll have 16, and then so on. So the only element I don't get prescribed here is if I have an infinite string of t's. So we're going to say that if I am so unfortunate to have t, 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 for this guy, we set x of omega to be 0. So as you can see here, this random variable, this is finite. There is no infinity value for my random variable here. Right? It takes the values 2, 4, 8, 16, 32, and so on. And if I compute the expectation, what would the expectation be? Well, if I compute the expectation of x, how is that going to be? Well, I'll write x here as I'll write x here as what? I'll write x as a I'm running out of space now. How could I write x? Well, I could look at I need a partition, so I could look at a let me do an A2. So this is going to be that set where those are those omegas where x is equal to 2. Where x is equal to 2, I could look at the set A4. This is going to be where x is equal to 4, and so on. And these are disjoints. These are disjoints, and I also need the last one when it's all equal to tails. Okay. So then I'll say what I'll say. What will I say? I'll say that the expectation of x is equal to, well, I'll write out what x is. It's going to be in sum. And then I'll have to index, I'll have to run my ends. I'm not going to specify exactly how the ends run because they go from 2, 4, 8, 16, and so on. So n belongs to 2, 4, 8, 16, and so on, of what will be the value, it will be n times the indicator for a n. Now comes the time where I need to use monotonicity. If I cut off here of the sum m, then as a function of m, this is monotone. Because I'm positive in here. So I can write this here as a sum over n in this here is monotone convergence. This is monotone convergence of n times, and then the probability of an. Because this was, after all, how I computed an expectation of an indicator. It's just the probability of the set. Okay, so now I'm good. What am I going to get? I'm going to get n starts out at 2 times the probability of an. Well, an, this is a, I get into an as soon as I have a head. So I have a fair coin. So say that the coin is fair. Fair, independent coin tosses. I'm going to get 2 times a half plus, and then the next one is going to be 4 times the probability of being up in this part of the tree. Okay, so this means I need a tail and then a head. Okay, so the independent half is going to be a 4 plus, and then 8 or 1 over 8 plus. So, and now you see they cancel out neatly. I get 1 plus 1 plus 1. This is equal to plus infinity. So what this example here shows is that it's perfectly possible to have a random variable which is finite, but its expectation is plus infinity. And it's not very far away from your homework 1, where you were looking at integrals from 0 to 1 of, say, x to the alpha dx. You could have that even though x to the alpha was finite, you could still have that this was plus infinity. This could happen. So it's not enough to have a function that's finitely valued, just as it's not enough to have a random variable that's finite. You can still end up with these expectations being plus infinity. Okay, now we're way over time. It's time to call it quits. I'm sorry I went over a little bit. But yeah, let me stop here, and then we can go and get something to eat. Good night, guys.
Thank you, Professor.
You're welcome.